Excellent. All right. So thanks for joining, everyone. Welcome to today's Open Neuromorphic seminar. And we're going to have Giorgia Dellaferrera presenting a new fancy forward-based deep learning algorithm called Pepita. So before we go there, just want to give a little bit of information on Open Neuromorphic, what we are. I guess once my screen wants to move to the next slide. So it's a nice little community created by open source enthusiasts. A few of us have developed fairly large code bases that we have a lot of people contributing to, and it's a platform for coding hardware projects. We're hoping to host these types of seminars roughly once every fortnight or so, in between some coding seminars and little hackathons. I guess it's just a nice educational platform for both, I guess, people that are getting into neuromorphics and people who are veterans in the neuromorphic space. We have a Discord server. You probably are hearing my icon kind of going wild right now. So feel free to join that. And I guess, yeah, it's a pretty cool place for neuromorphic folk to hang out. I really should mute that. We've got a few upcoming talks. I guess I'm coming up next with a hands-on coding session with DNNs for people that want to learn how to build hardware-aware spiking neural networks. And we have a few other presentations coming up, so feel free to check out our website or just go to the Discord for a full schedule. And so, yeah, with that being said, I'd like to introduce Giorgia, who just defended and successfully defended her PhD at ETH Zurich and IBM Research, where she currently is. And she's also a visiting researcher at Harvard. And also people who have alongside contributed to or led part of the Pepita algorithm. Ravi, who is a master's student at ETH, and Martino, a postdoc at ETH. And with that being said, I'd just like to flag that this session is being recorded and it will be uploaded to YouTube. But yeah, we can treat this as a bit of an interactive session. We can make it conversational. Feel free to write questions in the chat and hopefully I'll notice them and I can relay them to Giorgia. Or you can raise your hand and I'll pass you the proverbial microphone or something to that effect. So I'll stop sharing my screen. I'll hand it over to Giorgia and you can take it away from here.
Okay, sorry, I was on mute. Thank you for the introduction. Can you see my screen now?
Yes, all good.
Okay, perfect. So thank you very much, everyone, for coming. I'm really happy I'm going to share with you what we've been working on in terms of forward learning, especially in light of the hype created by the recent talk by Hinton. And I'm going to explain how we've been working on the Pepita algorithm and how it is a forward learning algorithm in which we have top-down feedback to create the modulated path. So I'm going to talk about the paper we published with Gabriel Kramer at medical school in Harvard last year at ACML, and our recent preprint that we just put on archive a couple of days ago. We have here Ravi, Francesca, Martino, and then there's other authors, Avi, Maria, and Gabriel, who couldn't make it. So I'd be happy to involve them in the discussions whenever there are questions. And as Jason said, please let's make this interactive. So in case anything is not clear, please stop me right away and don't wait until the end of the presentation. So before getting into forward learning, I want to motivate why we want alternatives to backpropagation. Some of them are not forward learning, some of them are forward learning, but let's make a little bit of history. Because I noticed that once Hinton came out with the forward algorithm, a lot of people were very excited about having an alternative to backpropagation. But maybe not everyone was aware that this has been a field quite hot in the past few years, and there are many other alternatives of backpropagations that have been proposed. So the story starts in 1989 when Rumeralt proposes backpropagation, encounters a lot of hype in the public, but only a few months later, Francis Crick comes up with a commentary in Nature in which he explains that yes, backpropagation is really exciting, but be careful, that's not what is happening in the brain. Learning is different in this backpropagation and in biology. And this is followed by a few reviews. Here I report a couple of more recent ones from Lillicrap and Whittington that basically try to explain how backpropagation could be implemented in the brain, but what is not biologically plausible. And there's a number of aspects that has been reviewed and criticized in the literature. I'm going to go through these in the talk, but basically the key message here is backpropagation is not biologically realistic. Let's come up with other ways to train artificial networks. And a few of these algorithms have been presented already a decade ago or so. And a milestone one is the feedback alignment. From now on, from 2016 on, I'm going to show just a few of the many algorithms. So this is not an exhaustive list. It's just, again, to remark that many biologically inspired algorithms have been shown before forward. And in parallel with the feedback alignment algorithm from the Lillicrap's lab, Podge and colleagues at MIT came up with the sign symmetry. And only a few months later, Nockland had a solo paper in Zurich extending feedback alignment to direct feedback alignment and indirect feedback alignment. 2 years later, the error forward propagation was able to solve to train recurrent neural networks. And the following year, in 2019, Charlotte Frenkel proposed direct random target projection, in which it uses the target instead of the error as modulatory signal, solving some of other biologically unrealistic aspects of backpropagation. In the same year, again from Lillicrap's group, Akroot proposed 2 ways to enhance feedback alignment, the Collen-Pollack mechanism and the weight mirroring mechanism that we're also going to use in the rest of the talk. 2 years later, from Gersner's group at EPFL, the CLAP algorithm came out, and from Sacramento and colleagues in ETH, the deep feedback control. Finally, we are at last year when Gabriel and I proposed Pepita at ICML, and a few months later, Hinton gave his keynote lecture on the forward algorithm. So these are just a few of the pieces of the puzzle composing this field. And today I'm going to focus mostly on 3 of them. So feedback alignment, Pepita, and forward. And we have a time scale of a few years, but I'm going to shorten it up to a much quicker time scale because machine learning is a very fast discipline. So the time scale of the talk today, we're starting now, we're going to be together for an hour or so. And my intention is to first detail a bit these algorithms independently. And then I hope that by the end of the talk, everyone in the audience will have a clear idea of how they are connected with each other. So how Pepita is an actual approximation of feedback alignment, and it is an implementation of the forward algorithm with top-down connections. And also, I want to show how these connections are useful to improve the performance. So given this connection, we can, for example, use an enhancement of feedback alignment, that is the weight mirroring, to also improve the performance of Pepita. So with this in mind, I'll give a little bit of structure of this talk. We will start again with a jump backwards to backpropagation, how it works, why it is not biologically plausible, what has been proposed as an alternative. So I've named a few algorithms before. And then I will show how they're connected. And we will go more in depth into Pepita, in particular on how we can use only forward passes to train neural networks, what this gives in terms of performance in benchmark tasks, how we can explain this performance, and also how we can characterize it analytically. And finally, how having this analytical work, how we can enhance the performance in a rigorously motivated way. In the third part, I will detail the forward algorithm, and in particular, I will focus on what are the similarities and as well the discrepancies with Pepita. And I will spend the last few minutes to connect again with biology, in particular on Pepita. I will take questions after, and then for who's interested, I'm going to give a short coding tutorial on how we can implement Pepita with PyTorch. I'm not a MATLAB fan, unlike Hinton, but this means we are on different grounds now. So, backpropagation. Just to be all on the same page, I'm not sure what's the background of the audience, but I might say the obvious, but backpropagation is the most effective training algorithm so far. It has been used in very, very complex tasks, achieving impressive performance. You may remember a few years ago where it was used to train a network able to play the Go algorithm and able to beat the human world champion. As well, it has been used to more creative tasks, such as producing works of art. So this looks very complex and abstract in some sense, but is actually based on a very simple algorithm, which is the chain rule that we learn in calculus. And it is used in backpropagation to change the parameters of a network, the synaptic strength, in order to decrease the network's error. And I will use a terminology repeatedly, so to be sure we are all in agreement with this. When I talk about credit assignment, I refer to assigning the blame to each parameter on the error. So how much we want to adjust a weight in order to decrease the network's error as a response to a certain input. And to do so, we need the notion of target, which is the desired output of a network. For example, the label of an image. We show in the MNIST dataset handwritten digits, and we want the network to output a certain number. We compare this with the output to obtain the notion of the error. And we use the error to update the parameters. The parameters are the weights, here indicated as W. And they regulate how the signal is transmitted from one node, so these dots here, that are grouped into layers, these green boxes. In terms of abbreviations, whenever you see DNNs, this is artificial neural networks. Then we have fully connected neural networks and convolutional neural networks. So how we use these notions for backpropagation? We alternate two phases in the training, a forward pass and a backward pass. In the forward pass, the signal travels from the bottom to the top layers. We have an input, for example, an image X. Using the weights W, we compute the activations H at each layer, and we compute the output at the end. Comparing the output with the target, we define the error, which we need to compute the weight updates that need to be proportional to the negative gradient. So in the backward pass, the second phase, we use this error information in the opposite direction. So now the information flows from the top to the bottom layers. And we use the transpose of the same weights used during the forward computation to propagate the error from the top to the bottom layers. At each layer, we use the chain rule to compute the update, and then we apply the updates in the update phase. So this has been very effective, as I mentioned, in very, very complex tasks, but still presents criticisms. Three of these fragilities are adversarial attack, catastrophic forgetting, and lack of generalization. Adversarial attack is the lack of robustness to noise. If we give a neural network the image of the pig, it is able to classify it very easily correctly. But if we modify this with minuscule noise that is not perceptible to the human, so that if we look at this image, it looks exactly the same as this image, the network output is quickly fooled into seeing an airliner. And this is the adversarial attack. The catastrophic forgetting is the inability of a network to remember tasks sequentially. So if we learn a task 1, for example, discriminating input class 0 from class 1, and then we learn another class where we want to learn digit 2 versus digit 3, then the network learns task 2 but forgets task 1. Third, it is difficult for networks to generalize. For example, if we train networks to classify animals in pictures, it will be difficult to generalize this knowledge into sketches. And last but not least, backpropagation is not biologically plausible. So while these may not matter for the user, so we don't really care if the algorithm in our phone is biologically plausible or not, developing algorithms that are more biologically plausible may give insight on why backpropagation is fragile under these three aspects. And backpropagation is not biologically realistic for at least 4 reasons. First of all, I mentioned we use the same weights to propagate a sensorial information from the bottom to the top and a reward information from the top to the bottom. And this means that backpropagation uses symmetric weights in a way that is not compatible with the brain dynamics. Indeed, in the brain, the synaptic path cannot be used bidirectionally and do not transport information of such different nature in exactly the same reciprocal path. So this gives rise to the so-called weight transport problem. Second, backpropagation is non-local. Indeed, we propagate the gradient from the top layers to the bottom layers, and there is no evidence that this happens in biology. So when we update, for example, W1, we need to have the gradient propagated all the way from the top to the bottom, and the information of the error is non-local, neither is that of the weights. Plasticity in the brain instead is driven mostly by local factors. Third, as I mentioned, we alternate a forward and a backward phase. In the forward phase, the network is responding to an input, so the layers are active, while in the backward phase, only the error travels through the network. This means that the nodes are non-active, there is no input being processed. And this is different from what happens in the brain, where the error information has been seen to modulate the activity and not to flow by itself in the neural circuits. And we refer to this issue as frozen activity. Last, the updated locking problem refers to processing a sequence of inputs and is related again to the alternance of forward and backward phase. In backpropagation, we need to wait for the computation of the error, which is called backward locking, error locking, in order to apply the updates. And the updates are applied from the top to the bottom. So when we process a sequence of inputs, X1, X2, X3, and we want to process X2, we first need to complete all the forward and backward steps for X1. While in the brain, learning and information processing happen simultaneously. So these issues, along with many others, motivated the community to develop alternative training schemes. And the first issues that the researchers tried to solve was that of weight symmetry. So having the same weights for the forward and for the backward passes. In 2016, Lillicrap came up with an idea to relax this constraint, which is that of replacing the backward matrices with fixed random matrices, here denoted as B, that are not evolving during training. The idea is that the forward matrices that are updated during training learn information about the B values so that as the training proceeds, the angle between the updates prescribed by feedback alignment and the updates prescribed by backpropagation decreases from a random initial value 90 degrees to around 30 degrees. This happens in 3 phases. First, while the error is propagated backward, the W's learn information about the B's. Then the W's are updated in order to align with the B's. And now the feedback alignment is basically an approximation of backpropagation, so that when the B's now send in the error information, this is useful for the learning of the network. And this was very successful, but still limited to very simple tasks and very simple networks. And about 3 years later, Akrut proposed to also train the feedback matrices using the weight mirroring algorithm. So we alternate a phase called engage mode, that is what I described, the training of the W's, with another phase that's called the mirror mode, in which we train the B matrices. And we want to do this without weight transport. So the idea is we give an input to an hidden layer, which is noise, a Gaussian with a certain variance. We measure the output at the following layer, where the output depends on the W matrix. And based on the input and output information, we create a signal which is proportional to the W that we can use to update the B without weight transport. And this leads to a very successful improvement, enabling feedback alignment to train ResNet networks on ImageNet dataset, which is much more complex than the scenarios explored before for feedback alignment. Jumping back in 2016, Nockland extended the feedback alignment to the case in which there are no reciprocal connections. In feedback alignment, all the nodes that are connected in a forward directions are also connected in a backward direction, just with different connections. In direct feedback alignment, the output layer is connected directly to each hidden layer, removing the constraint of having a reciprocal connectivity path. So these are just three of the many examples that I could detail to show that we can train networks without backpropagation, and they managed to solve the symmetry requirement. However, they still rely on a backward pass, and the backward pass entails the three other issues that are non-locality, freezing of the activity, and at least partial update locking, because we need to wait for the computation of the error in order to propagate it via the B matrices. So my intuition was, instead of training the network alternating a forward pass with a backward pass that can be approximated or not, let's simply remove the backward pass and only work with forward computations. And this is how the Pepita learning rule was conceived. So I'm now going to go to the second part of the presentation, related mostly to Pepita. Pepita stands for present the error to perturb the input to modulate the activity. As I mentioned, we want to remove the backward pass, and therefore we need to substitute it with something else, which in our case, we chose to be a second forward pass. The standard forward pass is the first forward pass and works exactly in the same way as backpropagation, feedback alignment, or other algorithms. The second forward pass, that we call modulated forward pass, instead uses a modulation of the input based on the error. So basically what we do is to take the error through a projection matrix F on top of the input. And projection matrix is, like in feedback alignment for now, random and fixed. The projection matrix is small enough that F times the error is much smaller than the input. So this is just a small perturbation. So we are performing two forward passes, one with a clean input, one with a modulated input, and therefore we're going to have slightly different activations. And we use this difference to drive the update. More in details, looking at the pseudo algorithm, we have the standard forward pass in which the input is X, for example, an image. For each layer L, we compute the activations based on a nonlinearity, ReLU in our case, but also hyperbolic tangent works, which is applied on the weights multiplying the activations of the previous layer. Then we compute the error as the difference between the target and the output, and use the projection matrix to take the error all the way to the input, perturb the input, and perform a second forward pass, where this time the input is X plus the error. So now, for all hidden layers, we have different activations, and we use this information to compute the weight updates. For the hidden layers, the weight update has the form of two factors. One is the postsynaptic term, in which we have information about the first forward activity and the second forward activity. And we multiply this by the activity of the presynaptic layer. So for W2, we only need information about H2 with the error and H2 and the activity at the previous layer. We can either use it with the error or without, empirically doesn't change. So what you see now is that the update is local because we only have information about the activity of neurons that are connected to the synapses. Only for the last layer, we use information about the error, as the error is locally accessible. So to keep in mind, this update is backprop-like or feedback alignment-like. And with this algorithm at hand, we tested it on different benchmarks from MNIST, so digit classification, to C410 and C400. And we tested both fully connected and convolutional implementations of the network. For now, we only use one hidden layer and one output layer, where the hidden layer has 1,024 neurons. We compare with three baselines. With backpropagation, we see that for all cases, we have a drop in performance, but it is just a few percentage points. And considering that Pepita came up as an intuition and backpropagation is an exact algorithm, we may consider this to be a small gap. When we compare with feedback alignment, which approximates more or less backpropagation, we see that this gap is reduced. For example, in the case of C400, actually Pepita performs slightly better. We also compare with direct random target projection, which substitutes the role of the error with the target in order to remove update locking. But this comes at the price of a lower performance. So we see that in all cases, Pepita outperforms also DRTP. And finally, we look at the convolutional version, and we see that it improves slightly the performance of the fully connected models. So these results were actually surprising at the very beginning. So we wanted to make sure that all the elements that we introduced in Pepita are useful and that we're not just training the last layer in a useful way and the rest is random. So we performed some controls. And you can see here the results on C410. For example, we removed the projection matrix. If we remove the projection matrix, we basically remove the perturbation of the input, which removes the perturbation of the hidden layers. So the differences that we have in the weight update are 0 now. And this means that if F is 0, we only updated the last layer. The test curve in this case is the yellow one. And you see that the results are much worse than with Pepita. So we need some projection. We need some modulation. But do we need a modulation that is random or do we need the error? To understand this, we remove the error and we perturb the input with some random perturbation, RP, which is just a vector with a different magnitude, K. And we see the training curve, the test curve, sorry, in green, purple, and pink here. And we observe that for all these cases, the results are much worse than with the original Pepita. We were very surprised, but also curious in trying to understand why this was working. So we took inspiration from feedback alignment and look at the alignment between the projection matrix that is fixed and the product of the forward matrices that are evolving. And we observe a soft anti-alignment phenomenon. This means that as the network accuracy is improving, the angle that at the beginning is around 90, so random, increases of about 30 degrees. And this is what has been observed with feedback alignment with the reverse sign. The sign here doesn't matter because instead of adding F times the error, we can subtract it as the mean of F is negative, and we would obtain alignment instead of anti-alignment. We were able to analytically prove this in the case of a linear network with just one layer, which is the same proof that Lillikrab did in his paper. But we weren't able at the ICML publication to prove why Pepita is actually working until I met Francesca at a conference. And then together with Maria, who had been working before on feedback alignment, she came up with an idea that led to show that Pepita can be approximated by a feedback alignment-like algorithm called adaptive feedback alignment. The idea basically takes the weight update that I've shown before and applies a first-order Taylor expansion. So for those who need a little bit of refresh of calculus, here I show that we take a nonlinear function f computed at a certain argument a, which is perturbed with a small perturbation h. If we look at this difference here in the updates, for example, for the first layer, and we expand the terms to show the role of the nonlinearity and the weights, the argument, so x, and the perturbation, we see that we have the same form. So we have a nonlinearity, the argument, and a perturbation. The perturbation in our case is much smaller because f times e has a magnitude which is much smaller than x. So then we apply to this term the Taylor expansion. So we have the function computed in its argument plus the perturbation multiplying the derivative in the argument. We notice that this term and this term are the same. Minus and minus gives a plus. And so we end up with this term here, where the derivative of the function is the activation prime. This term here has the form of feedback alignment. We have a matrix which is fixed, the f, like in feedback alignment was the b, times the error, times the derivative of the activation. But all this is multiplied by a matrix w that changes over time, it adapts. So this led us to call this adaptive feedback alignment. And what Ravi showed, and this is all contained in the preprint if you want to check it out, is that if you train a network with this approximation of Pepita to the first order, so with adaptive feedback alignment, the dynamics of the network is the same. This is on MNIST, but it holds also for CFAR10 and CFAR100. And as I mentioned, Francesca and Maria had previously looked into the analytical characterization of feedback alignment. So they applied similar tools to characterize adaptive feedback alignment, which is the approximation of Pepita. And this is done using a teacher-student setup where the data are generated at each step. So basically an input vector which is thrown randomly and fed to a teacher network with fixed weights that generate a label for each input vector. And then a student network is trained with our algorithm in order to learn basically what the teacher network is telling them. And this setup can be used to characterize the dynamics and look at the mean squared error. So in the limit, infinite dimensional limit of both input dimensions and number of sample, what Francesca did was to look at the error of Pepita in blue, adaptive feedback alignment in purple, and the theory used by integrating a set of ODEs. And what she found was an excellent agreement that characterizes analytically Pepita. She also looked at the dynamics of the angles by looking at the angle of the weights with the adaptive feedback matrix. So the F matrix multiplied by the change in W, the weights of the teacher network, and the weights of the teacher network in the closest degenerate solution. And this shows that for some steps, there is a plateau, and at some point, the weights start learning, leading to a decrease of the error. So this has shown that Pepita can be approximated with a feedback alignment-like algorithm. And this led to the intuition that since Pepita is similar to feedback alignment, and feedback alignment can be improved with weight mirroring, maybe weight mirroring can also improve Pepita. And to check this, we had to face a first challenge. As I showed in weight mirroring on feedback alignment, we need to give at each layer one input, a Gaussian input, and measure the output. And then we use information about this noisy input and the output together with a learning rate to update the weights for each layer. So we need a one-on-one correspondence between the forward weights and the backward weights, which, as you may remember, we do not have in Pepita, where we only have one projection matrix. So the idea here is that of factorizing the projection matrix into matrices that have the same dimensions of the forward weights. And then we can apply the weight symmetry, the weight mirroring in the analogous way of feedback alignment. What Ravi managed to show is that when adding weight mirroring, so the purple and pink curve to Pepita, we obtain a much better alignment than the vanilla Pepita here in light blue. As I mentioned before, we can flip the sign in order to have alignment instead of anti-alignment, like I showed before. And this was useful because we were able to do this for multiple hidden layers. In terms of performance, a better alignment translates to a better performance and also better convergence rate. I'm going to show here the performance. We see here again for one hidden layer and one output layer the results. We tried different enhancement of the performance. Adding weight decay, for example, already improved the performance. Adding activation normalization also improved the performance. But adding mirroring improved it further. So here you should compare this last line with the first one. You see there is improvement. Mirroring in combination with weight decay further improved. And mirroring in combination with activation normalization also improved. For example, for CFAR10, reaching almost 1.5% more than the vanilla algorithm. You may have noticed so far that I only talked about very small networks with just one hidden layer and one output layer. And here I've shown that activation normalization helped a bit the performance. And Ravi had the intuition, let's try to see if activation normalization also manages to train deeper networks. And this was the case. So on all the 3 datasets, the network managed to converge up to 6 layers. So 5 hidden plus 1 output layer. What we see, however, is that there is a slight decrease in performance, and which we leave for future work to improve. So wrapping up on Pepita, I want to now go towards the forward algorithm. And I've shown before that Pepita uses 2 forward passes, and I'm going to show that forward does the same, and that the weight update are analytically the same under some conditions. So the forward algorithm has again 2 forward passes. The terminology is a bit different. This is called positive pass if it goes on real data. So for example, a clean image of the MNIST dataset, and it's called negative pass if it is performed on negative data, in which this time the negative data is perturbed based on the labels. So we take a hybrid mask that takes part of the clean image, so you can recognize here the top of the 7, and then adds on top the part of an image of another class. So here should be the bottom of a 6, if I remember correctly. And given these 2 forward passes, forward tries to increase the goodness in hidden layers when the pass is the positive one, and to decrease it during the negative pass. More specifically, the goodness can be the sum of the square neural activities. So in the forward, we try to increase the norm of the activities, the square activities during the first pass, and to decrease it during the modulated pass or the negative pass. So now we pause for a second on the forward, go back to Pepita, and look at the learning rule. So as a reminder, we have the difference of the postsynaptic activities times the activity of the presynaptic node. We can rewrite it to just split up the difference, and we look at these 2 terms, and we approximate the first term by replacing the activity of the second pass with the activity of the first pass. Now we end up with 2 terms in the update. The first only has information about the first pass. The second only has information about the second pass. So there is no hybrid term as in the original version. We can also separate them locally. So we can update the weights already during the first forward pass, applying only the first term. And then in the second forward pass, we can use the updated weights, this W plus that we created here, and then apply the second term only with terms of the second phase. So this becomes time local, basically. We dub this first approximation the Hebbian, and we see that in terms of accuracy for 1, 2, and 3 layers, there is no significant difference between the original Pepita compared to the original Pepita. For the time local, instead, we have a big drop in performance. We have about 40% on CyPy. But now let's stick to the Hebbian and go back to forward. So I said we want to maximize the square of the activity in the forward pass and minimize the square of the activity in the negative pass. And this can be translated in a local loss function for each layer, in which we have one term that has the square of the norm activities in the first term and then the negative of the activities in the modulated pass. I'm not going to go through the derivation, but if we take the derivative of this loss with respect to the weights, we end up with these two terms. This is just for the forward. We have one term only with information about the first pass, one term with information about the second pass. And what we notice is that if we have a ReLU nonlinearity, the derivative of the activation is 1 if the activation is positive, and it is 0 if the activation is already 0. So basically, we can eliminate this term and have an exact equality in which the derivative of the loss with respect to the weights is two terms. One term with only information about the first activity, the other with only information about the second activity. And if we take back the Pepita Hebbian, you can see that it has the exact same form. So here a disclaimer, we are taking as a goodness the square of the activities. What Hinton introduces as well is a logistic nonlinearity and a threshold. So the analytical form of its weight update is different. This is why we're just saying that Pepita is equal to the forward framework with top-down connections, but the weight update is not identical in the case of the goodness that he chooses. There are, however, some differences. So first of all, the weight update is similar, but the way the passes, the inputs are generated is different. So in Pepita, we modulate it through the error, and the input looks very similar to the naked eye as the clean one, while the perturbation for Hinton's algorithm is much more pronounced. This also leads to a difference in the outcome of the algorithm. So we don't find any maximization or minimization of the activities between the first and the second forward pass. Here is the difference, and we see that it is centered in 0. So I've now connected the last piece of the puzzle, just a jump back to biology that we used to motivate the beginning of the talk. And I've outlined 4 issues of backpropagation, and we see that Pepita and forward solve them. So there is no backward pass, so there is no symmetry. The learning rules are local. We only need activities of nodes connected to the weight, so that's solved. The activity is never frozen because we only have forward computations, either clean or modulated. And for the update locking, we only need to compute the error. But as we have the error, we can update the weights in a forward fashion. So as we update W1, while we're updating W2, we can already start processing the input at the first layer. But Pepita specifically introduces introduces new elements that should be checked on the biological perspective. In particular, the introduction of the projection matrix is actually not an entirely new concept in biology, and it may be reminiscent of the connections that take information directly from the thalamus to the cortex in the cortico-thalamo-cortical loops. The second element that we introduced is the need of storing the activation of the first pass until the second pass. And this could be implemented using dendritic neurons. So instead of having point-like neurons, we have 2 compartments. The top is the dendrites. It integrates the information from the presynaptic layer, and then it sends it to the soma. When we have 2 forward passes, we can first store the information of the first pass in the dendrites and then send it to the soma. And then in the second pass, we first give the information to the dendrites. And before this information goes forward, there is a mismatch between the 2 compartment activity. And this has been shown to lead to a synaptic change in biology. So to summarize, I've talked about forward learning, in particular about Pepita and the forward algorithms that only rely on forward computation, substituting the forward-backward scheme with a forward-forward scheme. They managed to solve the mentioned issues of backpropagation, namely weight transport, freezing of activity, non-locality, and backward locking. And in terms of performance, they are similar to feedback alignment on this simple task, even though there's much to explore further. In terms of the relation between the two, we've shown that the weight update of Pepita is that of feedback forward under certain circumstances, and the equivalence holds where the modulation of the input comes through top-down feedback. In terms of Pepita, we've shown that we can analytically characterize its dynamic using an approximation that links it to feedback alignment, and that using this link, we can also motivate why weight mirroring improves its performance. We've just scratched the surface, though, what can be explored. Some criticisms relate, for example, to the lack of improvement in performance as we increase the network complexity, which we plan to address by looking into the introduction, for example, of residual connections. And finally, in terms of applications, Pepita as well as forward are not gradient based. This means that they may be more robust to the fragilities related to gradient of backpropagation. For example, what happens with adversarial attack, and how can we use them on video recognition, image recognition on videos. So that's a lot to explore further. And with this, I wrap up. Sorry, I went a bit over time. So this time scale was a bit more enlarged, but I hope I achieved the scope of the presentation, and I'm happy to take any questions.
Yeah, amazing. Thanks so much, Giorgia. That was really, really insightful. We had the Neuromorphic group chat going, yo, this is fire. This is awesome work. So yeah, no, thanks so much for I guess teaching us something really, really cutting edge in making backprop a little bit more, well, a lot more plausible, biologically plausible. So that, yeah, thanks a lot.
Thank you.
We have a question from Varshika, who's asking, is Pepita with weight mirroring also biologically plausible? Because weight mirroring with backward pass will have forward and backward sequence. So yeah, I guess, yeah, anything can be made more or less biologically plausible in a way, right?
Yes, I agree. So weight mirroring improves in terms of performance, but introduces the constraint of factorizing some connections that would be otherwise going directly from the top to the bottom. So that's problematic biologically. In my opinion, it is also problematic when applied to feedback alignment. So the way the authors justify it is the alternance of a wake and sleep phase, which interestingly is also the alternance that Hinton proposes for the forward algorithm. I'm not very confident that that's the most reasonable justification. So that's mostly to improve the performance. But I agree, it's an issue biologically speaking.
Yeah, in a way, it's also good to see it as an ablation study where you see how much impact weight mirroring has versus without. Like how critical is it to, I guess, doing functional tasks on, I guess, data-driven data sets. There's, by the way, yeah, we'll have a coding session as well. So feel free to stick around if you want to see Giorgia blast MATLAB a little bit more. So we've got another question. Just a basic question here. Someone wants to know, someone wants to get a better feel for biological plausibility. Can you explain it in simple terms? They tried to Google it, but it's not clear. To be fair, no one knows what biological plausibility. No, we have very measurable definitions of biological plausibility, right?
Yeah, so in our case, biological plausibility is defined as the negative or non-biological plausibility. So we don't really know how plasticity in the brain works, but we know how it doesn't work. So the issues I pointed out for backpropagation that have been discussed extensively in the literature relate to the aspects of backpropagation that are very unlikely to be implemented by the neurons. So the field of designing biological inspired algorithms goes in the direction of let's solve those issues. So the last papers that are coming out have this list of 5-6 issues, and then you show which algorithms solve which. and we are doing better because we solve one more. Basically, that's the trend of the field, at least how I'm seeing it. I think that until we have a clear idea of how the brain learns, which I don't think is going to happen very soon, then biological plausibility is just the opposition of biological unplausibility.
That's got to be my favorite response to that question that I've ever. Like that's perfect. Yeah, we know what the brain probably doesn't do, so let's just not do that. Sweet. So Fabrizio mentioned, do you have any? I guess he could ask it himself, but no, I'll do it for you. Yeah, do you have any theories as to why Pepita struggles on deeper architectures? I guess that, yeah, feedback alignment and all of the others also struggle on deeper data sets. Any theories as to why with Pepita?
Yeah, there's a big constraint that we only have one projection matrix. So there's not a lot of degrees of freedom that we can play with. For example, if you look at feedback alignment enhanced with weight mirroring, what you're doing is basically playing with a lot of matrices independently and aligning them to all the forward weights in an independent way. We are kind of doing that in the training phase, but as in the training phase of the Bs or of the Fs, but you still end up with only one projection on the error. So this is the most likely constraint of this algorithm. The other issue that is mostly technical is that you need to mitigate the explosions of the weight. So let me go back to a scheme of Pepita. Here, as you have a perturbation here, you go through a multiplication plus nonlinearity, another multiplication plus nonlinearity, multiplication plus nonlinearity. So you distort the input more and more, and the difference of the activations become bigger and bigger. So in order to get to the 6th layer training, Ravi applied activation normalization, which may result in some loss of information, but if you don't do that, you have explosions because this difference becomes too big. So this is why an idea would be to introduce residual connections and have, for example, blocks, or have partial stations of relay of the error so that they behave a bit independently.
Yeah, so activation normalization makes a lot of sense. I mean, the reason we went over to, I guess, Keiming-Herz initialization method was to get variance of activations to be set to 1 or something like that. So if now you're kind of using forward-esque algorithms to push activations and projections through multiple layers, then yeah, those also have to be normalized. But then what you're saying is that this could potentially conflict with how much kind of like information compression, maybe it's kind of a lossy mode of pushing weight updates through the network, like a bit of a trade-off now. So that's fascinating. A couple other questions have popped up. Maybe you did just address this, but Gregor's asking, so when exactly are the weights updated during Pepita?
So the algorithm now doesn't really care because we don't want to update it on hardware. So what we generally do is to perform the first pass and the second pass at that point. So this is my PyTorch code. We have all the weight updates and we apply them. But if you don't want to keep in memory the activations for so long, as soon as you compute the forward weight, the second forward pass at the first weight, you can already update it because you have all the information you need. And then you go to the second layer, and as you do the second pass, you can already update it and so on. So you can basically reduce almost by a factor to the number of computations that you need to wait in order to start the next batch of inputs.
No, that's very clear. So Gabrielle is asking, does Pepita function online? As in, I guess, do errors have to be associated with the inputs they were associated with if the inputs changed slowly? If so, could input and errors be continuously and separately executed?
Yes, so this is an interesting application that we still didn't manage to try. And having, for example, image recognition on videos. So you have a video, you have a lot of frames, and the frames are close in time. So they are most likely very, very similar to each other. So you can do the first forward pass on the first frame, compute the error, then you add the error on top of the second frame, and you do the second forward pass already with the second frame, with the error of the first frame, compute the updates, you get the error about the second frame, add it on top of the third frame, and go on. So backpropagation would need to do forward, backward, forward, backward. We would only need to do forward, 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 forward. But
yeah,
I haven't tried that yet.
In a way, it feels like that would work perfectly fine because you're exploiting temporal correlations in data, and it's just like another form of recurrence where F is kind of like a forward in time connection. So for the spiking neural network people in the crowd, that should be ringing research idea bells. Hey.
Yeah, that would be really cool. There's the big constraint that you need to have the frames to be very, very close to each other. Otherwise, the F times the error is not small enough or big enough, depending on the way you see it, to drive useful updates. But yeah, I think it's an interesting way. Another variation that you could try to make it, again, in a supervised context, but quicker, would be to put the target information instead of the error, so that you can do the forward passes in parallel, because the error is the target minus the output, where both are one hot encoded. So you're always going to have the same sign, but the error is a magnitude. So if you give the label together with the input, you don't need to wait for the error to perform the updates. You can just do them in parallel. But yeah, again, it's on the agenda of things to try out.
Yeah, I can imagine that's a very quickly growing agenda. It's just so many directions. We'll go with, so we'll have two final questions before we go on to coding and getting some interactivity going. Manuel is asking, well, he said, thanks for the nice presentation. So two questions. Have you assessed the performance under limited weight precision? My personal guess is that there's a lot of approximations being made here. Like this is already an approximation of gradient, or not of gradients, but if it's tolerant to that, then limited precision should be tolerable here as well. And secondly, might this algorithm be applied in single fully connected layers as in Hopfield models?
Okay, so for the first question, I haven't tried. I think the performance would decrease a little bit in terms of accuracy. It depends like what's the minimum value you have, because yeah, F times the error is quite a small value. So that might be an issue, but I don't know. And no, I haven't tried the second option you proposed.
Yeah, neural nets are already quite tolerant to limited precision, so I imagine it wouldn't be too far off. Another question from Christos is, so are you asking that are you saying that the error has to be backpropagated, whereas the target could be given in parallel? I think that's related to your previous answer.
Mm-hmm. So in this version, you need to do the first forward pass, compute the error, and then the error goes again goes to the input, and then you do a second forward pass. So you need to have the second forward pass happening after the first forward pass, because you need the error. It's not backpropagated, it's fed back to the input in a sort of recurrent way. The idea with the target is that you don't need to wait for the error. You can perform in parallel the first forward pass where the network is responding to X, and the second forward pass when the network is responding to X plus F times the target, because the target is something that's given a priori. So if you could, okay, I'm not really sure how you can do that on hardware, but I'm sure you can do this operation in a parallel.
Trying to figure out if it's me that froze or Giorgia that froze. Okay, so I think Giorgia's frozen. I'm not very good at improvising jokes, so in the meantime, so I'll go ahead and address another question while Georgia figures out the internet situation on her end. Oh, there we go. You saved me from having to do a stand-up comedy routine for everyone, so.
I'm sorry. Okay, so I'm happy my laptop waited until the end of the presentation. I'm restarting it, so then I can also show the code after, but I can continue answering the questions from my phone in the meantime. Sorry about that.
No, that's all good. Yeah, no, so yeah, while we get the coding sesh up and running, Ma is asking what types of loss functions are you considering for your experiments? I assume cross entropy.
Yeah, cross entropy and softmax as output activation.
Yeah, awesome.
Yeah, but I think Francesca can jump in. For the analytical characterization, she used the error function, if I'm not wrong. If you're here.
Hi, George. Yes. So for the analytic characterization, we are able to track the dynamics of the population error as a function of time in these specific settings where the learning is online. So there is basically no distinction between population. We cannot access the training error, only the population one, because at each time step we're given a new example. And I'm not sure, I mean, I got a bit lost when you froze, so I'm not sure what is the specific question I have to answer on the analytic part.
Sorry, it was about the output activation function and the loss function that we use for training.
Yes, the loss function is the mean square error, while the activation can be generic. We use in the evaluations that we have shown the sigmoidal activation, but other choices are possible, for instance, the ReLU. The advantage of using the sigmoidal is that in the system of ODEs that we have, at some point we have to compute different averages, and with the sigmoidal activation function, this can be done analytically, fully analytically. We have expressions which speeds up the computation a bit. While for ReLU, for instance, we have to use like a Monte Carlo method to compute the averages numerically, because there is no closed expressions. But in general, we can use quite generic loss functions, like activation functions and the mean square error loss, as soon as like the first two moments are well behaved, for instance.
Sweet. Thanks for that. By the way, sorry, Francesca, I didn't get to introduce you at the start just because I missed you. I didn't catch you in the list of participants. But no, yeah, sorry about that. Awesome. So yeah, I think that Georgia's got it, getting the coding session up and running. I'll throw one question if we're still getting things set up at you. How do you analyze computational complexity of these types of algorithms? I mean, it feels very obviously more efficient than backprop. We can do away with a lot of gradients, but then yeah, you see like backprop comparisons to real-time recurrent learning, where you've got something that scales with the number of neurons times, I guess, time if you're doing some recurrent training, and then real-time recurrent might be number of neurons cubic. So that's the computational memory complexity of those types of algorithms. Is there like a standardized way to compare these non-backprop type of algorithms other than accuracy?
I have not studied the computational complexity, also because in this this is a particular setting that's online. So basically there is no distinction between the training set size and the running time. And so I don't know. I mean, this type of analysis cannot be really done in general. I mean, I don't know how I would do this in general. And it also is in the scaling regime, where we have that the number of dimensions and the number of training samples scale linearly, and both tend to infinity.
Yeah,
So it's a quite specific setting, while things may change if we have different regimes of training set size and input dimension.
Yeah. It does kind of feel like, because these are such novel ideas, and they're really shaking up backprop based algorithms so much that we just the presentation of these ideas alone is really compelling. Then I also expect, since your work has come out and since Jeff Hinton has, I guess, broadcast to the entire deep learning community, we're going to see an explosion of these types of algorithms to follow over the next 3 or so years. And I guess once that happens, then it might be important to figure out. So yeah, I don't believe that there is any homogenized or standardized way to compare these types of algorithms, but it would be cool to see what metrics emerge to prove that they're not only accurate, but also potentially more efficient in online setups.
One of the metrics that is used also for spiking neural networks sometimes, so the number of operation might still hold. I've seen a post of like people playing around that was showing that the number of operations and the memory that you need at each step is not very favorable for forward for shallow networks, but it becomes more favorable for deeper networks. Then Pepita at least doesn't converge for very deep networks, so this is totally useless at this stage. But maybe in the future, this will become a bit more useful. I'm not sure what how forward behaves for deeper networks than those reported in the paper. But I think the same metrics for now are okay, and then probably something else will come up. Yeah.
So yeah, how are you going with the notebook setup? Any success?
Yeah, it's open. Yes, sorry about this. I'm in between jobs and I need to change my laptop.
Well, ETH.
Okay, so okay. So I guess you can see the notebook.
Yep.
Okay, perfect. It's basically the same notebook, just made a little bit simpler of the GitHub code that is in the first ICML paper. So there's this called Giorgia Dellaferrera. I have the link here. And there is, if you browse and you're interested, it is the tutorial Pepita fully connected nets. This is mostly the same. What I'd like to point out is that Ravi is a much better programmer than I am, and he did a code in PyTorch Lightning that takes half the time, if not less, than my code. And you can check his code on PyTorch Lightning. I think, Ravi, correct me if I'm wrong, there's a link in the new preprint that came out yesterday or 2 days ago.
Yes, exactly. The link is all in the preprint.
Okay, perfect. Okay, so most of the code is what you would do with backpropagation, just the weight update is different. So you start off by importing the libraries. In this case, I use Torch and other libraries that are commonly downloaded. Then you define your network. The syntax is exactly what you use for backpropagation, except for dropout. So I chose to show you what we have with dropout. The default value that we use is 0.9 of keep rate, and it improves your performance a little bit compared to not having dropout, which is the same behavior as backpropagation. So you initialize, in this case, we have 2 layers. The hidden layer dimension is 1024. The input dimension depends on the dataset. So here for the CFR10 dataset, we have 32 times 32 because we have the 2D dimension that's 32 squared. 3 is the number of channels. And then the last layer is 10, which is the number of output classes. So if you want to do CFR 100, make sure here you put 100. You can initialize the weights automatically or do it in a more manual fashion. This is how you initialize the weights using the uniform hay initialization. In the last paper, we also tried the normal initialization, which gave similar performance. The reason why we moved to the normal is because when we factorize the matrix, if you remember in the weight mirroring, we factorize F in the product of multiple Fs. If you multiply normal distribution, they still give a normal, but if you multiply uniform distribution, they don't give a uniform distribution. So that's the only reason why we changed. And then here in the network, we have the forward passes. As I said, for nonlinearity, we use ReLU, and this gives the multiplication of the input. The dropout is the only difference that we have compared to backpropagation, because we want to make sure that the mask of dropout in the first forward pass is exactly the same mask in the second pass, because you don't want the perturbation to also add on top of different nodes being dropped. And then, as I mentioned, at the end, we have a softmax as output nonlinearity. In this cell, we have the different hyperparameters, learning rate, how much we decay the learning rate and at which epochs. Here I just put 5 epochs, but we train generally to 100. The keep rate is on the dropout. And then we have different optimizers. For now, we try just vanilla SGD or SGD with momentum. Momentum helps a bit the performance. And for batch size, we use 64. We initialize the network that we've defined before. And the network still doesn't have information about the projection matrix. Here we call it B because F is used for functional, so we don't want to make mistakes on this. And the dimensionality of F is the input with the number of classes times the number of classes, because we go from the output to the input. And we need to use a very small standard deviation. We multiply everything by this factor that we searched empirically, so that the input, the error is small enough not to become too big for the perturbation, but is not too small, otherwise we don't have any update. Load the dataset in the same way as we do it for backpropagation. And then we need to use
0.05, that's like a pseudo learning rate for F alone. Is that
exactly?
Kind of...
Yeah. It's just to make sure that the FE is much smaller than the X.
Perfect, thanks.
Here we have the hook function that we use to store in memory the activations, because we need for the updates to have the activation of the first pass minus the activation of the second pass. Maybe there's a better way to do it, but this is how I've done it. And we take it for all the layers. We need to initialize the dropout. So this is conceptually not very useful. It's just a pass of one image in order to have the dimension of each layers when we want to define the dropout masks. Martino also had a code that's a bit more PyTorch-like. Here I do it manually. I use a list to store the updates so that we can apply momentum. And so we keep in memory what was the update for each parameter at the previous time step. And then we take these into account when we apply the current update. So this is basically for each layer, just initializing a list containing the values that we need. And here is the actual training loop. So we go over the number of epochs. We verify if we need to decay the learning rate at this epoch. Generally, we decay at 60 and 90, but this depends on the dataset. And here within the loop over the epochs, we loop over the batches. So this is just a standard way of doing it in Backprop. We get the inputs and the labels or targets. We flatten them. In this case, we are in a fully connected network. So we go from a two-dimensional input to a vector, and this is what the flatten function does. And we want one hot label. So if we have 10 classes, we're going to have a vector of zeros, and only one of these will be a 1, which is the value of the class. This is the time of creating the dropout masks. So for each batch, we have a dropout masks. This happens only if the keep rate is less than 1. If you remember, we in the previous cell recorded what are the activations, so the dimensions of the dropout mask that we need for each layer. And we just initialize binary masks with zeros and ones, in which 90% of the elements will be ones and the remaining 10% will be zeros. And so these DO masks will basically be a list in which the masks are for each layer. So in one hidden layer network, we only have one dropout mask. We don't have it for the last layer, clearly, because we don't drop out the output. And then we perform the actual core of the algorithm. So the first forward pass, it's exactly same syntax as backpropagation. We have our network. We give as input the current batch, and then the dropout mask is what we have as a difference. So we perform the forward pass, and we use again this loop to record the activations of all the layers, fully connected and convolutional. In the forward pass, we have computed the outputs that we compare with the target to obtain the error. And then this error, so the E in our slides, is then multiplied by the projection matrix to give the error that we add on top of the input. So the modulated input will now be the inputs. So we had what we had here, plus the error times the B matrix or F matrix. Again, forward pass, but this time the input will be the modulated inputs. If you remember before, we had, where is it? Here, we only had the inputs. Here we have the modulated inputs. In the same way, we record what are the activations in the modulated pass. And now we compute the update. So we have the delta W, which is the update that we compute, and the V that takes care of the momentum. So for each layer, we compute the update. If this if loop over depending on which layer we are updating. So for the last layer, in this case, if we have more than one layer, which is the case that we are in, we have the error times the activation of the previous layer, which is in our case the first layer. And if you remember in the presentation, I showed that we use the error just in the update of the last layer because it is directly accessible. If instead we're updating the first layer, the first term is given by the activation minus the modulated activations times the input. So this will be X. For the hidden layers, if we have more than one layer, we have the more general formula. This will be the difference in the postsynaptic activity times the presynaptic activity. So now our delta W all contains all the terms for all the updates for all the layers. And in the momentum case, we loop over the layers, use this VW all to keep track of the update with the momentum. So gamma will be the parameter of the momentum. This was the momentum at the previous time step, and eta is the learning rate. Delta W all is what we've just computed for each layer. And eventually we apply the update to the weights. So this is one epoch. We are looping over all the batches of this epoch. And after the epoch, we test it. This is exactly the same syntax of backpropagation. So you just get the test images and the targets, you flatten them again, compute the output, and get the accuracy. This is, I think, backpropagation tutorial on PyTorch, so nothing new, and we print it. And here I just run 5 epochs and plotted the accuracy going up. If you look at the GitHub, you have as a reference to, if you want to check if everything is okay, you have more or less all the accuracy that you should have if you have a correct implementation of at all epochs.
Great.
So
Yeah.
that's all.
Excellent. Oh no, sorry. Continue if you had more to say.
Oh no, that's all for the code. But if you have any questions, suggestions even.
Yeah, no, so yeah, feel free to throw in questions, suggestions, etc. But yeah, no, that thanks so much for stepping through that. So PyTorch Lightning is great for optimizing and all that, but I like seeing like into the mind of the programmer, right? Because yeah, then you get to break things down and truly understand it. One just loose idea I had. So you had the feedback or projection or whatever pseudo recurrent, I don't really know what to call it, matrix B or your F when we're not doing functional. Because that's directly connected to your output layer, I wonder if you could get away with doing like some sort of gradient-based learning only for the layers that are directly attached to your output, and then be able to make the case that, look, is the brain calculating gradients? I don't know, but could we at least get away with applying it to anything that's directly connected to the output? It's whether or not it's biologically plausible, yeah, okay, whatever. But at the very least on hardware, it wouldn't be that inefficient, right? Because you don't need to route a gradient over to all of these parameters. It's directly, it's already local to the output. I wonder if you could get away with that and then probably get much better performance as well.
So in your idea, you would mostly train just the output? Or I'm sorry, I didn't catch how you would train the hidden layers as well.
Oh, no, so you followed the hidden layers in the same approach that you've done, but you would have some sort of I'm not sure what the gradient signal would exactly come from. I mean, you would have the trade-off between calculating things locally versus probably accuracy. But I think that there would be scope to get away with doing some sort of gradient-based update on the feedback matrix, right? Just the feedback matrix alone. Does that kind of make sense? What does it sound?
I see. Okay, so like a way to update just the feedback in a. Well, it makes sense, yeah, because you're the idea. I never thought about that. It's an interesting idea.
Yeah. So like what I'm thinking of is, rather than going down the neuroscience route, so I'm a circuit designer by training, so I focus on hardware. I focus on what I can extract benefits from the power efficiency angle of things. So yeah, I mean, if it's local to the output, then we would love that.
That's a good point, actually. Another one to add on the agenda.
Yeah, you've got to have you got to start building up your own lab where you have all of these students just working on like one tendril of Pepita.
Yeah, it would have been nice for sure.
The academic dream. Are there any other questions, comments, feedback, etc.? Oh yeah, there we go. So we've got one question asking, when's the new paper code going to be available?
It is already. So if you go on the archive, let's see if I can find it quickly. It should be here. It's a Google Drive link. We don't have the GitHub yet, but you can check it here.
Awesome. Sweet. Yeah, thanks for that. Cool. Anything else out there? So yeah, I think Fabrizio also, yeah, he attached a link in the chat, so you're welcome to go check that out there. Cool. Well, yeah, so I think we can wrap it up there. I'm sure everyone learned something new. I certainly did. I guess thanks for giving up your Valentine's Day to do this.
It's okay. It's still 1:30 where I am now, so I have the rest of the day.
No, I mean, that's probably the only way for neuromorphic engineers and deep learning people to actually spend a Valentine's Day just listening to forward mode learning algorithms. Yeah, so we'll wrap it up there. Thanks everyone for attending. Feel free to get involved on the Open Neuromorphic channel to see what future presentations, talks, hackathons, etc. are coming up. And yeah, we can start recording. And thanks so much, Giorgia, Ravi, Francesca. And we've got a bunch
you.
of audience
Thank you
clapping.
Thank you for hosting.
Thank you.
Thank you so much for inviting and for all the questions.
Awesome. All right. Well, yeah, we'll wrap it up there.
Bye bye. Thank you.
Thank you. Thank you